So liquid chromatography. So in this module, okay, the following are the learning objective. Describe the principles of separations in liquid chromatography. Explain the fluid flow system, elution methods, and stationary phases that are used in liquid chromatography. Identify the basic components of liquid chromatograph and their specific function, and evaluate the applications of liquid chromatography in analytical samples. So if we're going to look at the chromatography, okay, we says there are two basic types that we have. We have the planar chromatography and the column chromatography. So if we're going to look at this difference between the two, the planar chromatography, that's the one that you get from the organic chemistry. You have the paper chromatography and the thin layer chromatography. Okay. Now in the column chromatography, the main difference between these three is, we could say, the mobile phase that they have. Okay. So there's a section in the module that describes gas chromatography and how they are of different times based on gas solid, gas liquid, and gas banded phase. So all the support are what we call in solid phase, but some of the support there are liquid banded, or we could say gas banded phase in solid support. Now, there's also a part in the module that describes the supercritical fluid chromatography. Now, in this module that I'm going to discuss today, we go on the so-called liquid chromatography. So there are, we could say, several ways to differentiate the liquid chromatography. So in liquid chromatography, we could say the mobile phase is a liquid. Okay. So these are the different types that you have. You can have the partition or liquid-liquid chromatography. You can have the adsorption, which is the liquid-solid chromatography. You can have the ion exchange, size exclusion, and we could say affinity. So if we're going to look at the classification of the column chromatography methods, in liquid chromatography, it could be interaction of your sample between the liquid and the solid phase, that's absorption. It could be a liquid-liquid interaction or liquid bonded interaction, which is partition chromatography, okay? Or it could be ion exchange, size exclusion, or affinity. For gas chromatography, it's your gas mobile phase passing through liquid bonded to a solid support, or you have a gas mobile phase that passes through a solid support that serves as your stationary phase. Okay, and third one is just supercritical fluid chromatography. So if we're going to look at the first type of liquid chromatography, this has something to do with adsorption. So when we're talking about adsorption, this usually the term that we usually describe is stick to the surface. So the solutes are separated based on their different abilities to adsorb to the support surface. That's why I told you, stick to the surface if you have liquid chromatography. Okay. Now, if you have partition, it's dissolved into the bulk, which we're going to discuss in the later slides that we have here. So in absorption chromatography, we use an underivatized solid support. Okay, and this is the oldest type of chromatography. This is what Tisiwet did when he discovered these chromatographic methods. Okay, it's the absorption type of chromatography. So if there is one that sticks to the surface, the other one is dissolved into the bulk. Or if the first one is adsorption, partition chromatography has something to do more on absorption. Okay. So solutes are separated based on their different abilities to partition between the stationary phase and the mobile phase. So in a partition chromatography, you use a solid support coated or chemically derivatized with polar or non-polar layer. And this is the most common type of chromatography at present. Okay. And we have a term for that, the so-called reverse phase chromatography, where the stationary phase is non-polar, and the normal phase chromatography, where the stationary phase is polar. Now, we can divide or subdivide partition chromatography into two, something to do with the liquid-liquid interaction and the liquid-bonded phase. So in the liquid-liquid, you have a liquid stationary phase that's retained on the surface of the packing by physical absorption. Okay? And liquid bonded phase, the stationary phase is bonded chemically to the support surfaces. So that's the difference between the two. Okay? Now, if we're going to look at the two common type of partition chromatography, as I mentioned before, we can have this reverse phase chromatography where the stationary phase is polar and the mobile, where the stationary phase is non-polar and the mobile phase is polar. So here, if we're going to look at reverse phase chromatography, A being the more polar or the most polar, will elute first because the most nonpolar is retained more in the nonpolar stationary phase. Now, in the normal phase chromatography, okay, the stationary phase is the polar, hence the most polar is the one that is retained the most and elute last. And the mobile phase is the nonpolar. Hence, C here, which is the most nonpolar, is the one that is eluted first. So we have adsorption, we have partition. Okay. The next type of liquid chromatography is ion exchange chromatography. Here it separates ions based on their different abilities to interact with the fixed exchange site. So you take advantage here between the difference in their charge. So you use an ion exchange resin here with fixed charges on its surface. So you can have cation exchange where the support material that you have is negative group, or you can have an anion exchange where the support that you have materials is with positive groups. Okay. Now in an ion exchange, this is usually used in protein purification. So example that we have here for an ion exchange resin is the carboxymethyl cation exchanger. So you have here a negative charge that targets the positive or charged or the cation thing. Now, if we want to target negative ion or the anion, one example that we have here is the diethylamino ethyl. Okay, so I would suggest you watch the video that is attached here. You can use ion exchange chromatography as a high performance and ion exchange chromatography. So here you can use this to separate an anionic analytes, which are either ions in their common form or analytes that can be ionized at high pH values, okay, carbohydrates at pH 12. So the high performance and ion exchange chromatography, they uses what we call the hydroxide-based eluents at high pH to produce an ions from analytes that would not be ionic or that would be anionic, that would not be anionic at neutral pH. Now, the other types of liquid chromatography is the size exclusion chromatography. Here, it separates large and small solute based on their different abilities to enter the pores of the support. So what happened here, the large solutes elutes faster than the smaller ones. Okay, you use here a porous support that does not absorb your solutes. Commonly used to separate biological molecules or polymers which differ by size. So we could say this is based on molecular weight. So what happened here when you separate them, the higher molecular weight substance, they just elutes faster compared to the smaller one. Okay, so if you're going to look at here, you separate the large and small solute based on their different abilities to enter the pores of the support. So you have your a porous support that does not absorb the solute. I have personal experience using this one when I was there doing my MS thesis. So they commonly use this size exclusion chromatography. They commonly used to separate biological molecules or polymers which differ by size or molecular weight. Okay. So if you're going to look what's happening here in the gel exclusion chromatography, so you have this mixture. So you have the higher molecular weight, which is the red one, and the low molecular weight. So if you passes it through, you could see the higher molecular weight or the bigger one eluted first compared to the small molecular weight, because the small molecular weight, they pass through the beads, okay, taking them sometimes, while the higher molecular weight or the bigger molecule, they just pass over the beads that you have. So the one that you can use here is the dextran, or it goes with the name Cepadex. Okay, so Cepadex G10, G25, G50, G100, G200. So the number that you have here is based on the range of the molecules. So the higher the number, the bigger the molecular weight that you use. You can also use the one that has polyacrylamide as the material, and the trade name that they have is this one. Or you can use the agarose, separose, 6B, 4B, 2B. The experience that I have is I use dextran and agarose to identify, to isolate a protein or a lectin coming from a sea cucumber. That's my experience in using gel filtration. Now, the last one that we have here is affinity chromatography. So what you have here is you separate molecules based on their different abilities to bind to the affinity ligand. So you use a support that contains an immobilized biological molecule. Okay, that's your affinity ligand. And you commonly use this to purify and analyze biological molecules. And among all the types of liquid chromatography, this is the most selective one, because based on whatever is your ligand, it will just target a certain analyte. Now, if we're going to compare overall the type of LC that we discussed, maybe this figure here will tell you what type of liquid chromatography you're going to use. And the type of the liquid chromatography depends on the molecular weight of the sample. So if you're going to use low molecular weight, then you can have adsorption or partition chromatography and ion exchange. If you need higher molecular weight, you go with the exclusion chromatography. If in terms of water solubility, you may use partition and ion exchange. If in terms of polarity of the solute, okay, you can go from the non-polar going to the polar. Or if it's an ion or non-ionic character of the solute, okay, it can be the ion exchange versus the partition. So within the partition, you have the reverse phase and the normal phase. So it's just depending on what you're going to do. So questions like this, we're going to discuss this during the synchronous meeting. Okay, so we in our what we call introduction to liquid chromatography, we said there's what planar chromatography and column chromatography. So let's try to look at the classification of column chromatography. This is according to the type of the fluid flow system. So the easiest one, or we could say the simplest one that we have here is the gravity chromatography. So this is what you did when you pack a column, okay? And we're going to discuss them one by one as we go on. Oh, so after liquid chromatography, we can have the low pressure chromatography, the medium pressure chromatography, including the fast protein liquid chrome. And then we have the high performance liquid chromatography or high pressure chromatography, which is the main topic in this module. Okay. And you also have the ultra HPLC. Now, if we go with the gravity chromatography, it relies primarily on the hand packed columns. So we have an experiment of this in analytical chemistry where we put an ion exchanger or an ion exchangers, and then we select what cation we want to, what we could use. Okay. So if you're going to look at the gravity chromatography, it relies on hand-packed columns. It well suited for a single step purification like dissolving or affinity application. This is simple and usually low cost. So you just have a column there, you pack it with the solid materials, and you pass whatever sample you want to separate. So it's a manual process requiring constant monitoring. You don't want it to dry. So you have to make sure as much as possible that you have enough solvent that you have there. It's not a high resolution method, time consuming, and reproducibility is an issue, especially if you don't take care of it. Okay, so reproducibility is an issue if care is not taken to normalize the method. Now, the other type of classification chromatography is the low pressure. Here, you have a system that operates at pressure that's less than 50 pounds per square inch or 3 bar. Often used for simple protein purification that do not require high resolution. It can be basic to semi-automated, and you can equip it with the gradient capabilities, detector bulbs, or fraction collector. Okay. And then we also have the medium pressure chromatography. So I think the difference between the low pressure and the medium pressure chromatography has something to do with how much pressure you operate. So here, you operate around 3,500 pounds per square inch compared to the 50 that you have in low pressure. And it also referred to as the fast protein liquid chromatography. It often includes column switching bulbs, advanced gradient capabilities, and multi-wavelength detectors like UV, conductivity, pH, and refractive index. It can be used for preparative and analytical chromatography of a wide variety, from non-volatile organics to nucleic acids, peptides, and proteins. So the next one, which will be the focus of the discussion later on this module, is the high pressure or high performance liquid chromatography. It's a powerful analytical tool providing high resolution and sensitivity with capacity to detect parts per billion levels. It works up to 5,000 per square inch. or 5,000 pounds square inch. Okay, and this is the main topic that we have on this module. Now, in some instances, they have developed this so-called ultra-high pressure liquid chromatography. So this has a higher pressure compared to the HPLC, okay, 600 to 1400 bar. And it's effective use with sub 2 micron particle columns. So you use high pressure because you have a smaller particles that you have in the column. But this pressure, high pressure, also results with run time that is higher than the Lilly HPLC without sacrificing the efficiency. And it also has a high resolution application over traditional HPLC. Their chromatogram is similar to GC compared to the LC. Now, for other information about the column chromatography, you can go to these resources, okay? And just watch for the announcement with respect to the quiz or problem sets that will be tackled about this one. So the main topic of this module is the high performance liquid chromatography. So if you're going to look at the liquid chromatography that you have there, you can watch the video that's shown in the link here. And after that, you should be able to tell the different component of the HPLC. So if we're going to look at the basic component of HPLC, so we have here the solvent, the pump system, the injection column, the injection system, the column, and the detector. So it's always like that. Okay. So the solvent that we have here, that would be our carrier, or that would be our mobile phase. Okay. So for gradient elution, we can use multiple solvent. For isocratic elution, we can use one solvent, or we mix already the solvent into one solution, or different solvent, mix it into one solution. Now, the solvent can only be carried using the pump system. So you have pumps that would give you pressure up to 600 PSI, and they are the one that will carry the mobile phase, and the mobile phase would contain your sample. So you inject your sample, okay, and once it's injected in the injector system, which introduces small volume of samples from 0.1 to 500 microliter into the carrier stream under high pressure. So once you inject your sample, the pump will push the solvents, okay, and carry your sample with the solvents to the column. So column can be what, 10 to 30 centimeter. It's not as, we could say, long as the GC. GC would have around 30 meters long, okay? And this column that's typically 10 to 30 centimeter in length, it contains a packing material that is around 5 to 10 micron in diameter. Now the detector that you have, you can have UV, IR, refractive index, fluorescence, conductivity, mass spectrometry, or electrochemical detectors. Diode array detectors are used when wavelength scans are desired. So if you're going to look at the basic components of an HPLC system, you have the solvent that serves as your mobile phase. So the HPLC pump will push the solvent, or will carry the solvent, okay? Once you inject the sample into the injector, both the sample and the solvent will pass through the column where separation takes place. Now, the separation is monitored by the detector. Now, depending whether you have a destructive or non-destructive detector, okay, it will go to the waste. So when you say destructive, your sample is destroyed, so you cannot recover it. When it is non-destructive, your sample can be recovered and used. Okay. Now, for you to monitor what is happening in the detector, you should have a readout system that tells you when peaks come out. okay, or when separation takes place. So if we're going to look at the mobile phase, so these are any solvents that you have. There are many types that are available. The residence times of the solute in the stationary phase depends on the mobile phase that you use. Adjustment of the mobile phase polarity is needed to achieve good separation. So these are the properties of the commonly used mobile phase. Usually, in the reverse phase that I usually use these three. Acetonitrile as one of the mobile phase, and then mix it with either with water or methanol. So the thing that you need to look at this in the refractive index and the polarity index that they have here. Okay. So if you're going to look at the polarity index, if you want to look at the mixture, so this is the formula that you use. So polarity indexes and the volume fractions that you have. So for the normal phase separation, okay, this is the formula that you use to determine if there are good solvents or not. Okay. So we're going to discuss more about this during our synchronous class. So as I have told you, the mobile phase is the one that will carry your sample to the stationary phase. Now, there's two, we could say, mobile phase system in HPLC. You can have an isocratic elution where the composition of your solvent is constant throughout the analysis. Okay, the use of mobile phases composition remains constant throughout the separation. So whatever the composition at the beginning of the separation process, it will be the same at the end. And then we also have this what we call gradient elution. So in the gradient elution, this is the process of changing the mobile phase solvent strength to enhance the separation of both early and late eluting solute. Okay, so if you're going to compare these two, gradient elution will generate a better, we could say, results compared to isocratic solution. Okay, so I'll try to show to you the difference of this during our synchronous class. So in terms of the sample injection system, okay, we usually use small samples from 0.001 to 0.5 ml into the carrier stream under high pressure. So the sample must pass through a filter to remove particles prior to injection. So the way that we look at this is we have the so-called guard column. Okay, so if you didn't filter it properly, the guard column will get what we call a lot of all those contaminants that you have. And the way we clean up our guard column is we just from time to time sonicate it to remove any of the interference or contaminants that are what we call collected through the guard column. So in the HPLC, we use a syringe needle, okay? HPLC syringe needle should be injection for damage. So the way that you inject your sample, usually it's not direct, okay? So if you're going to look at the injection system, it's some sort of a loop that you have. So if you're going to look at this, when you load the system, You load your sample from the syringe, okay? Not all of them goes to the column right away, okay? So in the sample loop, okay, it will be mixed with your solvent, okay? And once you have there, some of them can go to the column, okay? And some of them can go to the waste if you're going to inject the sample. So the way that you look at this injection system, so if you have it in the load position, the flow of the mobile phase from the pump to the column is isolated from the sample loop, which is filled using the syringe, okay? And then if you rotate the inner valve to the injection position, it directs the mobile phase through the small sample loop and into the column. And if you have time, I would say look or watch this video here in the link to see how the manual loop injector works. I think it's better if you see it real time on what is happening. So usually here, when we use our HPLC here, so the student would load, okay, or inject their sample, and then after injecting it, they manually say load, and then that's the time, okay, the mobile phase will carry the sample through the column. So in the column, this is, we could say, the heart of chromatography, and there are different types of column that we have, okay, and it's only a small one. It must operate in high pressure, usually constructed of metals, okay, so this metal outside, and typical dimensions that you have 10 to 30 centimeter long and 1 to 3 centimeter diameter. So the column contains the packing material which holds the stationary phase. So there are, we could say, many types of this packing material that exist. Okay, typically the packing materials are around 5 to 10 micron in diameter. So the one that I told you earlier, the guard column, is used to extend the life of the main column. So there's an extra small thing that you have before the column. So what it is to make sure to remove any contaminants that it has. Okay. So the card column introduced to increase the life of an analytical column. It removes the particulates matter, contaminants from the solvents, and sample components that bind irreversibly to the analytical column. So the guard column serves to saturate mobile phase with stationary phase and minimizes the solvent loss from the analytical column. Now the composition here is similar to the analytical column, large particle size to minimize the so-called pressure drop. Okay. Now, if you're going to look at the stationary phase, if you look at the physical properties that you have there, the packings for the modern liquid chromatography can be classified according to the following features. It contains rigid solids, hard gels, or soft gels. It should be porous, okay, versus the one that is pellicular or superficially porous materials. You have to take into consideration the spherical versus irregular shaped particles. And then you also have the so-called particle size. So among the most common, we could say, materials used as stationary phase is the so-called microporous silica particles. This is the most commonly support. Now the particles are particles are permeable to solvent. If you're going to look at this, it's around 100 square meter per grams of particles. And you only use this for pH that is higher than or less than 8. Okay. If you want to use a higher, we could say, if you want to use a material for higher pH, you can use the polystyrene particles, which is applicable for pH 8 to 10. Now, if you're going to look at the microporous silica particles, this is how they look like. Okay. So this is the most common support. Now the silica surface that you have, it has up to 8 micromole of the silanol group, okay, per meter squared. So if you have a silanol there, usually you have the presence of this hydroxyl group. So the silanol group at low pH, they are protonated. So they become an additional H there. And then they dissociate to SiO above pH 3. And then the exposed SiO group, okay, strongly retain the protonated bases. And this could lead to what we call tailing, as discussed in the introductory slide. Okay. Now, in addition to that, we can go to this bonded stationary phase. So as said in the previous slide, okay, the partition chromatography, which makes use of the bonded stationary phase, can be subdivided either into a liquid-liquid, where your stationary phase is held in place by physical adsorption, and the liquid bonded phase chromatography, where the stationary phase is attached by chemical bonding. It predominates over liquid-liquid because of the greater stability and compatibility with the gradient elution. So liquid bonded phase chromatography involves covalent attachment of the stationary phase, which yields a thermally and hydrolytically stable bonded phase. So if you're going to look at this bonded phase stationary material, okay, what happened here is the silanol that are usually exposed, you encap it with the chloromethylsilane, okay? So the way that you have here, okay, you form a bonded stationary phase. So the residual silanol groups on the silica surface are cupped with trimethylsilyl groups, okay? So you react it with the chloromethylsilane and it will eliminate the polar absorption sites that cause tailing, okay? Now, the common functional group for this bonded stationary phase, you can have a non-polar one. So you can have a C18, a C8, or a phenyl. So the octadecyl is the C18, octyl is C8. So I use both C18 and C8 column for my reverse phase HPLC. Now, if you have a polar phase, that can be an amino or cyano group, or we can also have this diol, okay? Now, if we're going to look at the column, it is affected usually by the temperature. You can hit the column, okay? But unlike the one in GC where you can go around 200 to 400, you cannot do it here in the LC at that high temperature, okay? So when you hit the column, so usually you can have a compartment. My experience, I was able to hit it until 45 degrees Celsius, okay? So what happened when you hit the column, it can decrease the viscosity of the solvent, which reduces the required pressure or permitting flow rate, okay? Heating the column also decreases the retention time. And this is good because that means you can run the analysis faster, okay? Now, the main reason why you want to hit the column is it improves the resolution, because a higher or a high temperature stationary phase, they would hasten the diffusion of your solutes. But unfortunately, this is not commonly done because it can degrade your stationary phase and it will decrease the column lifetime. You seldom do heating of the column in HPLC, okay? But if you do that, it's because you have reasons. But usually you don't do that because the lifetime of your column decreases. Now, detectors. So everything we could say differs on the detectors. So we have this definition of the ideal detector. So an ideal detector should have high sensitivity and the same predictable response. As much as possible, you want your detectors to respond to all solute, or else they have predictable specificity. Okay. It should have a wide range of linearity. It should be unaffected by changes in the temperature or the mobile phase flow. It responds independently of the mobile phase. Because sometimes some detector, you change the mobile phase, they also change the signal that they have. Okay. Or when you have a gradient system, when the composition of the mobile phase change, it gives you peak, but the peak is not due to the samples or the analyte that you're targeting, but because of the changes in the mobile phase composition. Not contribute to extra column band broadening, be reliable and convenient to use. It should have a response that increases linearly with the amount of solute. So the higher the concentration, the higher the signal. As much as possible, it's non-destructive, so you can still recover your column and make use of it. Provide qualitative information on the detected peak, and most importantly, it has a fast response. Okay. Now, unfortunately, we don't have this so-called universal or versatile column, but we can divide the column that we have into three types. We have a general column, the specific one, and the so-called hyphenated detector. So when we have a general column, that's the one that responds to the mobile phase bulk properties, which vary in the presence of the solute, like your refractive index. You can also have a column that's specific. It responds to some properties of the solute not possessed by the mobile phase, like UV absorption. Now, if you have a hyphenated one, so usually this is the one that is attached, okay, like LCMS, GCMS, but we're talking about HPLC here, so we will say, yeah, LCMS, the best example here. Hyphenated, the one that has a hyphen thing. Now, the first type of the detector that we have is this so-called absorbance detector, or the UV detector. Okay, so it's the single most used and versatile detector in modern LC. Now, UV-based source usually comes from a monochromator, so the wavelength can be selected or scanned. The absorbance would increases as LU weight passes through the cell. If the wavelength scanning is desired, the flow is stopped long enough for the scan to take place. Okay, so it's just like this one. You have a UV source, and then there's your sample being carried by the mobile phase. So what happened? So the UV source passed through it, and then the detector would detect it. So once there are some chemicals that you have in your mobile phase, okay, and it absorbs the UV or the visible thing, you can detect that material. So absorbance increases as the LU weight passes through the cell. If the wavelength scanning is desired, the flow is stopped long enough for the scan to take place. You can also use IR as your detector. It's possible to have the same setup using IR, although this is not common, since many useful solvents are what we call not IR transparent. So most of the time, you can also detect your solvent when you use IR as your detector. Now, the characteristics of the UV detector, it's capable of very high sensitivity, but sample must have UV absorption. We use this in our experiment, HPLC analysis of caffeine in soda. Okay, so we were able to determine caffeine because it absorbed some UV region. Okay, 200 something. It's a good linearity range. It can be made with very small cell volumes with a small bond broadening influence. It's relatively insensitive to the mobile phase flow and temperature changes, except at high sensitivity. It's very reliable and easy to what we call operate. It's a non-destructive sample. It's widely varying response for different solutes. Gradient elution is capable, and the wavelength can be selected. The potential disadvantage of using UVBs is the widely varying response for different solutes. You can tandem this one in what we call LC. Since this is non-destructive, so it will pass through the UVBs detector, okay, the sample is still intact to be analyzed in mass spec. Now, a much higher version than your what we call UVBs is if you have this diode array detector. At least in the diode array, you have these photodiode arrays. They can simultaneously monitor more than one absorbing component at different wavelength. Okay, because if you have this UVBs absorbance, you target a certain wavelength through the monochromator. But if you have a diode array, it can monitor the different wavelength at the same time. So this provides many benefit of time saving and cost reduction of on expensive solvent. Okay. Now the diode array detector, DAD or PDA, they are used for simultaneously monitoring of more than one absorbing component at different wavelength. And this really provides benefit of time saving and cost reduction, especially when you're using expensive solvent like acetone. So the example that you have here, okay, so you have here what we call one that can be detected at 445 nanometer. So this is the chlorophyll that you have, the lutein and the beta carotene. And I would suggest you to watch the video here, okay, to know more about the PDA or diode array detector. Now the other one that we have is the second widely used detector in LC. That's the refractive index. Okay, so in terms of the refractive index, it monitors the difference between the pure reference mobile phase and the column effluent. Okay, so you have to know here what we call review Snell's law. So the way that it works, it responds to all solute if the refractive index of the solute is significantly different from that of the mobile phase. So for instance, you have some sort of a reference cell and a sample cell. So what's the difference of the reference cell and the sample cell? So the reference cell, you only have the mobile phase. In the sample cell, it contains your sample. So there's a difference that they have there. So if you're going to look at the refractive index of it, if it's the sample cell contains only the mobile phase, it's just a straight line. But if you have your component in the sample cell, you could see that there's changes in the what we call incident beam. So there's bending of incident beams due to the refractive index difference between the two solvents. What is the difference? Because your solvent now contain your what we call sample. Okay, it is good. It has an excellent versatility It can detect any solute. Its sensitivity is moderate for the solutes, generally not useful for trace analysis because of its high detection limit. It's an efficient heat exchanger. Efficient heat exchangers is required, and relatively it's insensitive to the mobile flow changes if properly thermostated. It's sensitive to temperature changes. It's reliable, fairly easy to operate. Unfortunately, you can only use it for isothermal elution. If you use it for gradient elution, you lost this thing here, because what happened in gradient elution, your composition changes. So that changes in composition mess up the principle, because the reference cells will change, okay, with the sample cell. So whatever you have in the reference cells, so usually maybe the original composition. So once you change the composition, it might pick it up as a difference on the refractive index as a signal. Okay, so as long as it's isocratic elution, same composition all throughout, it's fine. Okay, but if it's gradient elution, this is not a great detector for it. And the good thing about this, it's also non-destructive. So one thing that we can also look at is the fluorescence detector. Okay, it's more sensitive than the UVBs, but unfortunately, this can only be applied if your sample is fluorescent. I use an LC that we have there in the Philippines, Shimadzu in IC. I don't know if it's still useful. So it's very sensitive and selective detector for fluorescing solutes because of its ability to measure energy emitted from certain solutes excited by UVB. So usually you have here an emission wavelength and an excitation wavelength. So in the excitation wavelength, that's the wavelength wherein you apply the energy, and the emission wavelength, that's where you monitor any emission that came out once you excite it. Okay. So its main application is in biological sample, pharmaceuticals, foods, and fossil fuels, and in environmental testing. As long as the sample is, we could say, fluorescent, then this type of detector is useful. Okay. Now, another thing that they use is the evaporative light scattering detector. It responds to any analyte that is significantly less volatile than the mobile phase. And the response here is related to the mass of the analyte and not the structure or molar mass of the analyte. Okay. The light source that you have for the evaporated light scattering is usually a laser. Okay. And the good thing about the if you use evaporative light scattering detector, there's no solvent front peaks. Now, another one that is useful is the so-called electrochemical or amperometric detector. So the way that it works is look at the current. Okay. So the effluent from the column passes over the working electrode, which is held at a constant potential relative to the downstream reference cell. Okay, and what happened here, if your sample is completely oxidized or reduced, okay, the analyte, you're going to generate a current between the working electrodes and the referring electrodes, and you measure this as a function of the applied voltage. So this is, we could say, putting electrochemistry in HPLC. Because if you're going to look at HPLC, HPLC is just really a separation technique. Okay, so we're going to have some work here like quiz or problem set. So this is all for liquid chromatography. I hope you watched the videos associated on this what we call module.